This is the first of a series of lectures on special relativity. The prerequisites for this are linear algebra and multivariate calculus. The entire series is more geared at a mathematical introduction to the subject rather than a physical one. For the first lecture, we're going to examine the Lorenz transformation. The first thing we're going to do is we're going to define axioms which are needed to derive the Lorenz transformation. And we're going to do this derivation for inertial velocities that are in the direction of one of the axes, in this case, the x1 axis. After that, I will present the results for the more general inertial velocity in an arbitrary direction, and then show how this can be reduced to the former, and that gives a without loss of generality argument that the velocity may as well be only on one axis. Once you have the Lorenz transformation, it is easy to derive length contraction and time dilation formulas that are common in relativity. This is the basic setup. There will be references to two different frames, K, which will be considered to be stationary, and K prime, which is moving relative to K with a constant velocity V. There are space-time coordinates where T and Cartesian X coordinates are lumped together. And if there's a prime on any of these things, that means we're referring to a coordinate that's in K prime. If there's no prime, it's a coordinate in the reference frame K. What are the axioms? Well, first axiom, which is seldom stated explicitly, is that there's some invertible transformation between the space-time coordinates in K and K prime. That is to say that the coordinate K in K prime is some function of the coordinates in K. This is what's responsible for the mixing of the space and time coordinates in interesting ways in special relativity. In general relativity, the function phi is non-trivial. However, in special relativity, there's an additional assumption of linearity, namely that straight paths observed in frame K get mapped to straight paths in K prime. Consequence of that is that the aforementioned transformation phi must be a linear transformation. And lastly, and most importantly, is the axiom that the speed of light c measured in each inertial frame is the same. It is this last one which gives rise to the formulas for Lorenz transformation. How is that done? Well, this picture represents the following scenario. You have frames K and K prime, and at time t equals 0, these two frames coincide with one another. In particular, you could imagine that the sphere on the right is coinciding with the sphere on the left, and then as time progresses, these frames move apart. For the observer in K, this sphere represents light rays emanating from the origin in that frame. And therefore, in the frame K, we see these light rays must be on a sphere of radius ct. But according to the axiom, the person or observer in K prime must observe the same thing, namely using its coordinates, the prime coordinates. There should be an observed sphere of light that lies on a sphere of radius ct prime. Now, T and T prime need not be the same here, and that's what's crucial. And why it's possible to make it so that in either frame you see spheres that start getting larger. This is enough to derive the Lorenz transformation. It's one picture. Let's start. Okay, so the velocity here the velocity of the inertial frames will be in the x1 coordinate. And we know that it's a linear transformation between the space-time coordinates in k and the space-time coordinates in k prime. Since it's linear, there must be some matrix that defines the transformation. This matrix, we know a fair amount about at the start, namely that because the velocity is in the x1 direction, the x2 and x3 components will not be affected. Therefore, there must be a block identity matrix in this matrix, capital lambda. However, we do not know what the block is in the upper left portion of this 4x4 matrix. We have 1, 2, 3, 4 unknown coefficients. And the goal here is to find out what those are. To find them, we start with the fact that, well, the light emanating from the origin in K prime lies on this sphere here, x1 prime squared plus etc. equals c squared t prime squared. Now, if we have this transformation, the x1 prime can be rewritten in terms of the x1s and t's of the k coordinate. And how do we see that? Well, it's this second row here that I'm highlighting that tells you what x1 prime is with regard to x1 and t. In particular, this x1 prime will get replaced by lambda 10 t plus lambda 11 x1. Likewise, on the right-hand side of this equation, this t prime is determined by the first row of the Lorenz matrix, and it's going to be lambda naught t plus lambda naught 1 x1. This has got to be true for all t's and x1s. In other words, what's got to be true is that this thing has got to collapse down to this last expression saying that in K we see a sphere of a different radius, namely CT instead of CT prime. But if you take this middle expression and you expand it out just with algebra, you're going to have x1 squared terms, you're going to have x1t terms, and you're going to have t squared terms. And the coefficients of those will all depend on the coefficients of this matrix. And they'll give, in particular, like if you look at this last expression here, in front of the x1 squared term, there's a 1. So if you look at the expression above, I've got to find all of the ways that I can get x1 terms out of this expression. And then I'm going to have a lambda 11 squared. And then on the right side, I'll have a c squared times lambda naught 1 squared that I bring over onto the left side. And then that'll give me an equation for a couple of coefficients to make sure that this first thing in front of x1 squared is a 1. If you do that, you've got the x1 squared term gives you an equation. You've got the cross terms, x1 t's, there aren't any, so that coefficient should be 0. And then there's a coefficient for t squared, which should be minus c squared. This is 3 equations for 4 unknowns. There's 4 coefficients in the matrix that are unknown. So that's not enough. We need one more equation. To do that, we simply note that we know by the definition of the problem that the origin in K prime is always fixed in that reference frame. x1 prime is equal to 0, that origin is fixed. But that means in the k prime, it is given by the formula x1 equals v times t. So what does that mean? X1 prime has got to equal 0, and this is x1 prime, represented in terms of the k coordinates. If I use this x1 equals vt in here, I simply get a coefficient times t, and that's got to vanish for all time t. So that gives us this third equation in blue down here at the bottom for the coefficients of the Lorenz matrix. So that means I've got 1, 2, 3, 4 blue equations for 1, 2, 3, 4 coefficients in for the lambda ij's, and you go ahead and solve it. And this is just algebra. We won't do it here. The result is that you get this matrix. In particular, the upper left coordinate here has got a value of gamma, where gamma, this very common occurring term in special relativity, is 1 over the square root of 1 minus beta squared, where beta is the non-dimensional velocity, v divided by speed of light, c. This gamma term occurs in each of the 4 spots here, but there's these little extra terms on the off-diagonal terms of this little 2x2 block. If you look at this matrix from a mathematical point of view, it says, well, it's nice, but it's not symmetric. It's not aesthetic in that way. So we'd like to get a form which is symmetric, and we'll come to that very shortly here. Before we move on to that issue, I will just simply point out that you can take this matrix and you can, because there's this identity down there, we don't need to transform those coordinates. We only need to transform x1s and t's when we're going between frame k and k prime. So if you take this matrix, you can write this transformation in component form. And what you get is the following. So from that matrix equation, you write down, well, t prime is, here's the formula involving the t's and x1s in frame k. So I call this the forward transformation. So if you know what's going on in k, you can find out what's going on in k prime. Also, you can invert these things. It's very simple. It's a linear 2x2 linear system. So in other words, if I know what's going on in k prime, I can find out what's going on in k. These will be useful later. Next, let's go on to the issue of, well, do things change if I change the inertial velocity v? In other words, we're going to consider this case where the inertial velocity v is some arbitrary constant direction. You can rederive the transformation formulas if you do everything in vector form. For example, like a light sphere here is given by this norm squared is equal to c squared t squared in k, where v, this non-boldface v, is the length of the vector v. And if you do that, we will do it here, but if you do that, and Moeller has done this in 1, you get the following formula for transforming x and t spacetime coordinates to x prime t prime coordinates. When you look at this result, what you should see is that this is still a linear transformation, as it looks like there's like these squared terms and gamma is kind of complicated, but as just simply as equations involved in x and t, this first equation, for example, is linear in x. It's got a complicated term here. But what you can do with these two formulas is you can rewrite them into a matrix form. So this is for the most general v, and I can take this and figure out what the new lambda matrix would be to transform k coordinates to k prime coordinates. Now we're going to do that, but just before we do it, I want to introduce a slight change in the coordinates. We're going to create a new coordinate system. It's called Minkowski coordinates, where the first term is not t, it's actually c times t. Since t is time and c is the speed, the units of this first term will now be space. So this is a space coordinate, not a time coordinate. If you make this very small change and you use that formula on the previous page, then I can get the matrix that transforms S coordinates in K to S prime coordinates in K prime. And the result is this matrix below, which looks messy and complicated. It's got a lot of little nonlinear terms in it, in particular, things like v1 squared over v squared over here and gammas, etc. But if you look at this thing, one thing that immediately pops out is that it's symmetric now. As large as it is a symmetric matrix. That's useful because we know that things can be diagonalized, and it has real eigenvalues and all sorts of nice properties. So from a mathematical standpoint, when you're looking at this transformation, what you really want to look at is the eigenvalues and eigenvectors for this matrix lambda. And we'll do that. If you get lazy and you use something like software like Maple, you can easily find the eigenvalues of this 4x4 matrix. And there are 4 of them. There's this lambda 1, a lambda 2, and then lambda 3 and 4 are both equal to 1, so this is a repeated eigenvalue. But all 4 of these are positive eigenvalues. The matrix is symmetric, therefore the matrix is positive definite as well. Knowing these eigenvalues, it's just a bunch of algebra. You can figure out what the eigenvectors are. And eigenvectors are not unique. And here I present one aesthetically pleasing diagonalizing matrix comprised of columns of the eigenvectors. So the first column is the eigenvector of lambda 1, the second column is the eigenvector of lambda 2, etc. This thing, again, this particular matrix, if you examine each rows and you take the dot products of each rows, you'll see that they are indeed orthogonal to one another. For example, the second and third columns, if you dot product, you get 0. Same thing with the third and fourth. So what's going on here in third and fourth in particular is that I've got a 2-dimensional eigenspace for the repeated eigenvalue 1, and I have 2 orthogonal vectors here that span that space. So what does this all mean? Well, this is a without loss of generality argument. We may as well just have diagonalized the matrix and use the coordinate systems in that matrix S instead of our original ones and say that the velocity is in the direction of x1. Well, how do we do that? Well, all the eigenspaces are invariant, but the one that has lambda equal to 1, it's a 2-dimensional eigenspace, and every vector in there is unchanged by the Lorenz transformation. Every single one, because the eigenvalue is 1. There's no stretching, nothing. So if I have a space-time and Minkowski coordinate times lambda, it's just going to stay the same in the K prime coordinate system. So because of this special type of invariance, the Lorenz transformation acts in non-trivial ways only on a 2D subset of the Minkowski spacetime. So without loss of generality, we may as well have just a velocity in the direction of x1. And if you do that in the Minkowski coordinates, then the Lorenz transformation has a very, very nice form. It has the same gamma as before, but now these off diagonals are the same. Therefore, this whole matrix is symmetric, and that makes a lot of the math later simpler. Let's talk about length contraction. Well, now that we have the Lorentz matrix, we can derive the length contraction formulas that one commonly sees in special relativity. How do you do this? Well, you take you imagine a scenario where you say have a ruler in K prime, and the ruler sits on the x1 prime axis as it's drawn here. It has a left endpoint at point P prime and a right endpoint at Q prime. In this reference frame, this ruler is fixed to this axis. It's not changing length, and its left and right endpoints stay the same to any observer in K prime. That is not what is seen in K. But we know how the coordinates in K prime get translated to coordinates in K. That's the inverse Lorentz transformation. So what you can do is you can say, well, if I know where P prime is in K prime, and I know where Q prime is in K prime, I can use the inverse Lorentz transformation to find out what the preimage of P prime is. Call that P. The preimage of Q prime, call that Q. And that makes a little ruler along this x1 axis that's sliding along. And we want to know what the P and Q are so that we can figure out what the length over here is. So in summary, we've got this point P prime and Q prime. We know their coordinates, you can write them down, and we know in particular that this second coordinate is xp prime plus L prime, where L prime is this fixed ruler length here. And my goal is to find out what this new length L is. All you do is you just take these coordinates, P prime and Q prime, and find out what P and Q are with the Lorentz matrix. Rather than use the Lorentz matrix, we're going to just use the component form of the transformation. So if we have that, we know that this length L prime in K prime is the coordinate of the right endpoint minus the coordinate of the left endpoint. And I use the Lorentz transformation in component form here to find out what the preimages of xq prime and xp prime are. So that gives us x prime and p prime. So we just figure out what that is. So xq is this expression here, and then xp is this expression here. You subtract, and you notice that you get xq prime minus xp prime. That's just L prime. And the VT terms cancel. So the result is the length observed in K, that would be L, is the length observed in K prime divided by this factor gamma. And since gamma is bigger than 1, if you look at this expression, it's always bigger than 1. That means this value here is being divided by something bigger than 1, making L smaller than L prime. That's length contraction. Namely, if you have a ruler of fixed length in K prime, to the observer in K, it will appear to be shorter. Time dilation is very similar. What you do here is you say, okay, we're going to imagine two events where a light flashes at a time P prime, and then it flashes again at time TQ prime, but at the same location. So I'm sitting there in K prime and I see a flash, and then I see another flash. So the flashes occurred at the same point, but at different times. So those are two different space-time coordinates that you can use and find the preimages of those, just like we did before. Except what we're interested in is the difference in the time coordinates, not the space coordinates. So you use the Lorenz inverse transformation here to take the prime coordinates and compute the non-prime coordinates of time. And there again, you just simply subtract the t of p and t of q to find out the duration between the light flashes in the k coordinate. And you get another very similar looking thing. It says that if I measure the time between flashes in k and divide by gamma, that's what the time will be observed in k prime. And there again, given that gamma is bigger than 1, that says that the time in k prime appears to be, the time durations appear to be shorter than they are in k. So time passes more slowly and not to the stationary observer. All right. Last thing here is on this issue of time dilation, there's sort of a neat, very simple thing you can do. And this is to introduce something called inertial proper time. So I've got two frames that move with respect to each other with a velocity v with this component in the x1 direction. Then if that's the case, the inertial proper time tau is going to be the k time divided by gamma. So this is a new time tau. And all it is just scaled by a constant gamma in this case because v is constant. So if you have this tau time, then a difference in tau will agree with the difference in t prime in k prime. So what this effectively means is that you can be in the frame k and measuring your time durations in time t, and you can have a watch that moves, just has it moves slower by a factor of gamma, and you can look on your watch and it'll tell you what the delta t is, and you'll know what the observer in k prime is reading on their watch. It is simply just time tau. So that's going to be much easier to talk about things later. In particular, we'll say things like to the stationary observer, the proper time in the moving frame is something or other. And that means that we're saying that we know that in the other frame, the time is a scaled quantity. That is the end of this lecture. And